So can you send one's last lecture notes, session 6?
Yes. Actually, session 7, 6 and 7 have been on 3rd and 4th. So I have to send both of those notes. I think they're pending. I'll send them together. Okay, so today then we will start with the next portion of physics. Okay. And that is system of particles.
Center of mass, sir?
Yeah, center of mass is a part of this. So this is a very long section actually. It starts with the definition of center of mass. Then from there it goes on to motion of center of mass, and then from that the concept of linear momentum and impulse momentum theorem for a system. And from that the situation where we can apply momentum conservation including collisions and all that. And this chapter ends with collisions then. So the whole chapter is called system of particles. The first section of this chapter is center of mass, which we will begin with today. So center of mass in itself is like almost like a chapter in itself actually, but we treat it like a portion of this section, system of particles. So first of all, let's understand the definition, the word meaning of the term system of particles. So as the name suggests, it's very simple. Any system consisting of multiple particles is called a system of particles. So basically the mass of the system is distributed. Then we say it is a system of particles as opposed to an individual particle. So there is distribution of mass within the system. You can say distribution of mass over the space occupied by the system. So basically anything that consists of mass in practical physics ultimately is a system of particles. For example, whether we are talking about any rigid body, which obviously consists of infinite particles, but they are attached rigidly to each other, like a rod or a cylinder or a solid sphere or a hollow sphere, anything like that, a cube, any of these kind of rigid bodies, even an irregular shaped rigid body, it's a system of particles. But again, system of particles need not be rigid. It can also be a system like this, like a gas inside a container. That's also a system of particles. It's a non-rigid body, but it is a system of particles. Okay. Any fluid, that's also an example of a system. Or we can also have a system like this where we have a collection of particles, like you can say tiny dust particles on the surface of a table. That's also an example of a system of particles. Okay. Or we can have a system consisting of many rigid bodies. Okay. So it could be, for example, the carom coins. On a carom board, or snooker balls on a snooker table. These are all examples of different types of system of particles. So we are seeing that not only a rigid body is a system of particles, but we can also have a system that consists of multiple rigid bodies. Like if you consider a system which consists of all the snooker balls on a snooker table, and each individual snooker ball in itself is a rigid body, and our system consists of multiple rigid bodies. The solar system is an example of a system of particles. Okay, it's a gigantic system of particles in comparison, but would again be an example of mechanical waves.
Molecule is also a system of bodies.
Very correct. Okay, so in that sense, now what happens is if you really start asking yourself that, okay, all these things are system of particles, then what is a particle itself? Then the question to that is unending, because You can break down molecules into atomic particles, which you can treat like particles, but then you know that atom can be broken down into subatomic particles. The nucleus can be broken down to subnuclear particles, and then that story goes on till you reach the fundamental uh, particles of matter or the fundamental particles of physics. And that list of fundamental particles also keeps changing with time, because physics keeps advancing, so that we are able to break down the most fundamental particles into further smaller particles. So that's an unending story, that what is a single particle at the end of the day. But here, okay, let's say that we are talking about Newtonian mechanics or classical physics, where we're talking about what we call a macroscopic system, not so much a microscopic system. So you can treat a molecule as a particle also, or you can even treat a cluster of molecules like a particle, depending on how we're trying to define a system. If we can even treat, for example, in my example that I've taken here, the snooker balls or the carom coins on a table, we can actually treat each carom coin as a particle. If our scale is sufficiently large enough, if our geometrical scale is large enough, like let's say the carom board's surface is of the order of probably a couple of meters square or something. So compared to that order of magnitude of distance or geometrical length, the diameter of a carom coin can be considered small enough to treat it like a particle. So it's really a matter of perspective, what we are treating as a single particle, and therefore what is a system of particles. So in the end, like if you really talk about fundamental particles, then everything is a system of particles. It's very difficult to isolate a single particle. Okay, understood the point? Okay, now based on this sort of definition of system of particles, now we will classify system of particles into two categories. We will classify them. So I'll give you time to note down, don't worry, but just let's finish the classification part also. Then we can start with center of mass. So any system of particles, it can be classified as one of two types. One is called a discrete particle system. So what does the term discrete mean? It means individual or isolated. So this is a system that consists of individual isolated particles. So for example, I could have, let's say, two particles of mass m1 and m2, and I've joined them together with a comparatively very light rod. So compared to the mass of the particles, the mass of this rigid rod joining them is negligible. So I can say my system consists of just the mass of the two particles m1 and m2, and the system's mass is distributed such that there are two individual points where the mass is present, m1 and m2. It's distributed over two individual points. It's not continuously spread out over space, because this is a light or massless rod. So this is an example of a system, a discrete system of just two individual particles. So like that, I can have any number of particles like that. Whereas the other type of system that we'll define, the other second classification of system of particles, will define that as what we call a continuous mass distribution. Let's look at that definition. So this is such a system where the mass of the system is not located at discrete or individual points, which are particles. Rather, it is distributed over a continuous geometrical space. What type of spaces depend on what type of system you're talking about. Okay, so this is a system whose mass, total mass, is distributed continuously or contiguously, you can say, over a certain geometrical space. So example, any rigid body is an example of a continuous distribution of mass. Whether the rigid body is a linear shape like a rod, okay, or it is like, let's say, a ring or a disc, okay, or it's, let's say, a cube or a cylinder, whatever be the case. But everywhere we are talking about mass distributed over a certain region of space, a certain amount of volume, a certain amount of surface area, whatever be the case. Okay. Then gas trapped in a certain container. That's an example of continuous mass. Okay. Gas or fluid, whatever be the case. These are examples of continuous mass distributions. Okay. So I will just give you a minute to go through this section, including the definition of system of particles and then the classification of system of particles. And then we'll come to the first important aspect of system of particles, which is the center of mass. How we define center of mass, how we write a formula for center of mass from which we can mathematically calculate the position of center of mass. All these things we'll discuss.
Sir,
Yes.
so suppose there's a chain, so that could be considered as either a discrete or a continuous, right? Like we could either consider.
Yeah, so it depends on our scale of measurement. Like, suppose the chain consists of links, okay, and each link has a diameter which is of the order of a centimeter or something, all right, or even an inch or something. But the chain is very long; it's a meter long or something, and our scale of measurement is such that compared to that, the diameter of the bead or the diameter of the links of the chain is very small. You understanding? Then we can treat each of the links like particles.
Yes. Okay, sir.
So what we can treat like, very small, or what we can treat as very large, or what we can treat as infinitesimal, what we can treat as infinite, what is a point mass, what is a distributed mass, it often depends on the scale of our measurement. Because ultimately physics is a subject which has to do with measurement of physical quantities. So it all depends on our scale of measurement of physical quantities. Okay, hope it's making sense what I'm saying here.
Yes, sir.
Okay. So I'm now scrolling down to the classification of system of particles with the examples. Okay, so let's now come to the definition of center of mass for a system of particles. Now that we have understood system of particles definition and also some examples with also classification of system of particles into discrete versus continuous.
Last few examples are remaining to write possible.
Now, what we'll understand is whether we are talking about a discrete system or a continuous system. Every system has a particular special point which is defined as the center of mass. So let's see what is the definition of that center of mass, and let us see how to calculate the position, how to find out the position of the center of mass given any kind of system.
Done. Sir.
Okay, done. Good. Just a moment. So I will just send you the recording and the link and the notes for the 3rd December session, which was circular motion session number 6. I'll send 7 also in some time. You can reference these and complete problems of circular motion from H.C. Verma, both from the chapter of circular motion as well as the additional questions of vertical circular motion, which are in the next chapter, which is the work by energy chapter. So complete all these problems in this week at least, okay, if not by tomorrow, because we have a session tomorrow. You might not have time to finish everything, but finish by next week so that one of the lectures next week we can devote for any discussion of doubts and questions from circular motion pending. All right, now here let's, as discussed, now talk about the center of mass of a system of particles. So quite a few lectures we will spend on the concept of center of mass and all calculations related to center of mass now. So center of mass is a special geometrical point within any system of particles, and that special geometrical point is defined in such a way that we say the mass is distributed symmetrically with respect to center of mass. Okay. So center of mass is a geometrical point within a given system of particles such that the mass of the system is distributed symmetrically with respect to that point. So this is a very qualitative definition, because what we exactly mean by symmetrical, that is not clear from the definition itself. But as we take examples and develop some mathematics for it, it will become more and more clear for us that what we mean by symmetry, that what type of symmetry, how we can claim that the system is the mass is distributed symmetrically without with respect to what we call the center of mass. So let's understand that next. Okay. So we will explain this symmetry business by taking a few examples along with the definition. So for example, if I have a system consisting of two particles, A and B, but they are of identical mass m, and the distance between them is L, then we can all safely understand that the center of mass should be by default the point which is the midpoint of these two, because that's how the symmetry of mass is. There are two particles of equal mass on either side of this point, which is equidistant. So therefore, this must be the symmetry point. So we'll define the center of mass for a system like this as its midpoint. Okay. So for a system of two identical particles, A and B, of mass m each, the center of mass will be at their midpoint, C. Okay. But similarly, if now instead of two particles, I had four identical particles, which are located at the corners of a square. And they may be joined by rigid rods, they may not be also, they might just be individual particles that are just lying at these 4 points, P, Q, R, and S. So as long as they are of identical mass, then we can say that the center of mass will be where? It will be at the centroid of the square, which we can get by either looking at the intersection point of the diagonals, or that is the same thing as the intersection points of the perpendicular bisectors of the sides. So when we have equal mass particles, it's quite easy to define the center of mass, okay, because it is the centroid formed by the figure made by them. So at least in terms of a discrete system consisting of identical masses or identical mass particles, it's quite easy to define the center of mass. It is defined geometrically as the centroid. Okay. So 4 identical particles. P, Q, R, and S, mass M each. Okay, placed at the corners of a square. The center of mass is at the centroid C of this square. So these are 2 very intuitive and simple examples to try and get a sort of intuitive feel of what we mean by the term symmetrical distribution with respect to center of mass. That the mass of a system must be symmetrically distributed with respect to center of mass. Centroid of a square is the intersection point of its diagonals and perpendicular side bisectors, both. Okay, now let's understand that obviously all systems will not consist of identical mass particles. So if the particles are of different mass, how would we calculate the position of the center of mass? So our next example, we will take again a two particle system, but this time, let's say particle A is of mass 3m, whereas particle B is of mass m only. Okay. And the distance between them is L. So what do you think should be the position of the center of mass now?
Should be at a point that is in the ratio 1:3.
1:3.
It's very good. So not only do we know by just looking at the system that because A is heavier than B, the center of mass should be closer to A and further away from B. But we also know that A or B के mass का ratio क्या है 3:1. So the center of mass is distance from A to B, from A and from B should be in the inverse ratio of that. So that means the distance from A should be 1/3 of the distance with respect to B, because the mass of A is 3 times. Okay. So if A is of mass 3m and B is of mass m, okay, so there's a two particle system. So that means the center of mass should divide the distance between them such that EC is to CB will become 1:3, because mass of A is to mass of B was equal to 3:1. So the center of mass should be somewhere here, such that this distance now will therefore become L by 4, and this distance will be 3L by 4. So if AB is equal to L, that means AC will be 1/4 of L and CB will be 3/4 of L, because AC is equal to 1/3 of. So now we can generalize this. Now we can say for any two particle system, any general two particle system, if one of them has a mass m1 and the other one has a mass m2, and the distance between them is L, then the center of mass should be such that this distance, let's say R1, and this distance R2 are such that R1 is to R2 will become M2 is to M1, or M1 R1 is equal to M2 R2, and R1 plus R2 is equal to the length. So just note down this example, and from this do a calculation that what are R1 and R2 in terms of how will we express the values of R1 and R2 in terms of the distance between the two particles L and the masses M1 and M2. Yes, very good. That's correct. Or you can use component or dividend and all that. Okay. So thus your answer is correct. So I mean, it's not that difficult really. It's very simple calculation. So you basically use this statement that R1 is to R2 is M2 is to M1. Okay. So that means, for example, R1 is equal to M2 by M1 times R2, and R1 plus R2 is equal to L. So substitute this here. So you'll get the value of R2. So that is one way of solving it. So you need not necessarily apply component or dividend. You can just get it this way. So R1 will be equal to M2 upon M1 plus M2 into L, whereas R2 will be M1 upon M1 plus M2 into L. Acha, there should have taken M1 upon. Okay, so it will be M. Just flip the numerator. Anyhow, so now what we will do is we will write the same formula that we have for a two particle system in a slightly different way. We will write it in the coordinate geometry method. So center of mass of a two particle system in coordinate geometry type of notation. So we are going with the coordinate geometry notation. Since it is just two individual particles, we can take our x-axis as the line joining the two particles. Okay. So let's say the individual particles are located here. Mass m1 at x equal to x1, and second particle mass m2 at x equal to x2. So the center of mass of this system should be somewhere in between the two of them. So now you'll see that this will come as m1 x1 plus m2 x2 divided by m1 plus m2. Because once again, divides the line joining them. Such that inverse of the ratio of the masses. Hence, so from this formula, we can look at another way of defining the center of mass of a two particle system. It is the weighted mean. It is a weighted mean of the individual coordinates. So m1 into x1 plus m2 into x2 divided by m1 plus m2. Instead of just x1 plus x2 by 2. If it was x1 plus x2 by 2, we would have said it's the mean of x1 and x2. But it is the weighted mean with respect to mass. Means that we have to give weightage to the mass of each particle when we are calculating the weighted mean. Okay. And obviously, if the two particles have identical mass, then it will become the arithmetic mean position. But otherwise, it will always give more weightage to the mass which is heavier. Okay, now even this formula can be converted into a three-dimensional notation or a vector notation. So Cm of or center of mass of a two particle system in vector notation. Now let's understand that. Begin with, let's take a 2D system. So we have two individual particles, say A and B, of mass m1 and m2, which are located on a two-dimensional plane. So their individual position vectors are given by these vector arrows. So let's say this is at position vector r1 and this is at position vector r2. So you can say r1 is like this and r2 so this is at position x2 y2, this is at position x1 y1. Now the center of mass of this system will lie on the straight line joining AB such that, as discussed, it divides that straight line in the inverse ratio of their masses, or divides the distance between the two particles in the ratio of their masses. So let's see how we'll incorporate that now. So the center of mass should be, let's say, somewhere over here. Center of mass, such that its position vector now we can write like this. So because EC is to CB is going to be M2 is to M1. Therefore, x coordinate of the center of mass is going to be M1 x1 plus M2 x2 divided by M1 plus M2. Y coordinate of the center of mass is going to be M1 y1 plus M2 y2 divided by M1 plus M2. And the position vector of the center of mass is xc I cap plus yc j cap. So when you compare this equation with these two, you can see that we can write the position vector of the center of mass in vector notation as m1 r1 plus m2 r2 divided by m1 plus m2. So this becomes a vector definition. This again the weighted mean of the individual positions r1 and so with this we have both the type of notations using a single axis and coordinate geometry or using the vector position vector notation. We can later extend this to 3 dimensions also, where the individual particles are having all three coordinates x, y, z. So the position vectors are having three components x I cap plus y j cap plus z k cap. Then also this definition will be intact. It will be in the same way that RC is equal to m1 r1 plus m2 r2 divided by the summation of the mass.
Done, sir.
Okay, so let's look at our first problem involving this. Okay, but we'll just make a note of the fact that if we are talking about a 3D system, then also the formula remains the same. So in the general 3D case, all we have to do is add the z coordinate. But in terms of the vector notation, it's very much the same formula. If A is a particle of mass m1 at x1, y1, z1, and similarly B is a particle of mass m2 at x2, y2, z2, then the position vector of A will be written as x1 I cap plus y1 j cap plus z1 k cap. The position vector of B will be written as x2 y2 z2. Then the center of mass of AB as a system, as a two particle system, is at position vector RC, given by again the same formula m1 r1 plus m2 r2 divided by m1 plus m2. And this statement now means that the center of mass is located at some coordinates xc, yc, zc, and individually and the other two are also similar formulae. So this is the general 3D case. Now let us look at our first numerical example using the definition of center of mass of a two particle system. So two particles A of mass 1 kg and B of mass something unknown are located at say 1 comma 3 and minus 2 comma something on the xy plane. Find mass of B and the y coordinate of B if their center of mass is located at the origin of the xy plane. Very straightforward question. You have to just apply the above definition, and that too is reduced to 2 dimensions again. No z coordinates involved. Okay, so just apply the formula of center of mass, that concept, and find out the answer quickly. Okay, so let's look at the answers. Mass of B should be
2 kg.
mass of B should be 0.5 kg.
And so y coordinate should be -6.
-6. That's correct. Very good. So this is the answer you should be getting, that mass of B is 0.5 or half a kg. Okay. And the y coordinate of B should come as 6. Because see, basically what is happening, center of mass is at origin. That means x of the center of mass is 0, y coordinate of the center of mass is 0. So that means mass of A into XA plus mass of B into X of B divided by MA plus MB should be 0. So this is my equation 1. And this should also be 0. This is my equation 2. So from equation 1, you can see that when we substitute the values, we have 1 plus minus 2 times MB divided by 1 plus MB is equal to 0. So that means 1 minus 2 MB is 0. So mass of B is half or 0.5 kg. Now from second equation, when you substitute the mass of B also, you have 3 plus 0.5 YB. So B is 0.5 kg located at minus 3 comma at minus 2 comma minus 6. So your whole situation is looking something like this. This is our XY plane. Then A is located at 1 comma 3. Let's say that somewhere here. Now B, it must be located somewhere here. It's half the mass, so the distance has to be double. That is why this is minus 2. This should be minus 6. Geometrically, this is what your situation will look like. That is a condition for the center of mass of the system to be at the origin. This is 2:1 ratio. Okay, so this is a very simple and direct application, like your junior college or board level question.
Done, sir.
Okay, now let's move on and look at how to calculate the position of a multiple particle system. That is no more than two particles. If we have like a many particle system up to some large number of particles, how we'll find the position of the center of mass. Formula for center of mass for a multiple particle system. Let's say we have n number of particles. So let's say with respect to our general three-dimensional coordinate frame now, our particles are located at various positions. So we have, let's say, particle M1 located at X1, Y1, Z1, particle M2 located at X2, Y2, Z2. And like this, we have all over three-dimensional space, large number of particles located at positions which are individually known. Okay. So the position vector of the first particle for particle M1, like that R2 for particle M2, like that in general, some index I. So that position will be given by xi cap plus yij cap plus zik cap for the particle mi. Okay, so here I is the index. Okay, so here I is going from 1 to n. The last particle in our series will have a position vector Rn, which is for the particle of mass Mn. So the center of mass of this system now will be given by the general definition that it is the weighted mean position. So the center of mass is somewhere here. So this system's center of mass will be located at position vector Rc. So the formula for this position vector is now going to be that it is going to be the weighted mean of all these positions. So when we write it as a vector formula, we will get this relation that position vector is M1 R1 plus M2 R2 plus M3 R3, like this. This series summed up to the last particle divided by the total mass. The last mass. Or we can write it this as a summation formula. So it is summation of mass into position, and the index is going from I equal to 1 to n divided by the total mass, which is nothing but summation of mass. Again, index I going from 1 to n. So this is one way of expressing it. Or if you want to express this in scalar form, we can say that x coordinate of the center of mass is given by summation mx divided by summation n. Y coordinate of the center of mass is given by and z coordinate is given by summation where everywhere here the index is going from 1 to n. That's understood. Okay, so I'll just take you to the top of this page once more. So understand first of all the definition of a many particle system and the method of the indices to represent them. Okay. Then we come to the definition of the center of mass as having a position which is the weighted mean position of the individual positions from R1, R2, R3 up to Rn. Yeah, but there is good question that you have asked, that what is the significance of this position of center of mass. So we'll see there are various different significances. For example, when we want to understand the gravitational force acting on a body, we'll understand that there is some position called the center of gravity. Now center of gravity has a certain relationship with center of mass, and we'll discuss about that at a later stage when we are discussing about gravity later. Okay. Or for example, if we are looking at a situation where we have a system of particles which are all moving about, and we want to apply impulse momentum theorem to that whole system, then we'll have to understand how the center of mass moves. What is the acceleration of the center of mass? What is the momentum of the center of mass? In order to be able to apply dynamics and concept of impulse and momentum to the system. So to be able to apply those things, we must know what is the definition of center of mass, and we must know how to locate the position of the center of mass. So it has significance when we are applying dynamics to any system of particles.
Okay, sir. Done, sir.
Done, sir.
Done, sir.
Okay, now from this, let's look at a couple of examples of how to find position of center of mass. Now we'll start using the formula. Okay, but along with that, we'll also see that whether we can use symmetry and superposition and simplify things in certain cases. Okay, so the next example we'll discuss is going to be about that, how we can simplify the calculation of center of mass for a many particle system by using some kind of symmetry that the system may have. So this is an equilateral triangle. Which represents the corners of the triangle represent the positions at which three individual particles are kept. So though the triangle is highly symmetrical because it is equilateral, but the particles we are keeping are not going to be symmetrical in that sense. So this particle A is of mass 2m, whereas these two other particles B and C, let's say, or B and D, let's say, are of mass m each. So we have to locate the position of the center of mass. of a system of three particles A, B, and D as shown in the diagram. So what is the position of the center of mass? Let's find that out here.
Done, sir.
Sir, I've sent you the answer in the chat.
Okay, so I'm going through the answers that people have sent. Okay. So we will see that the center of mass. So first I'll give you the answer. Okay. Then so it will be located on this perpendicular bisector. Okay. But at a point like this, it should be here, which won't be the centroid of the triangle because the three masses are not equal. So basically, this distance will be L by 2, and this distance will be root 3 by 4L. So one way to do this question is
3
to
by
just
2L, na?
No, half of that beta. We are at the midpoint of the root 3 by 2L is the whole altitude, but I'm saying where the center of mass is located. Okay. So one way to do this question is that you can take this point as your origin where B is located. And you can just use the formula. So if you take this as your XY system, you can solve the problem this way. I'll also show you an easy shortcut method of doing this using symmetry. But let's first understand the formula based method. Okay. So here the x coordinate of the center of mass should be MAXA plus MBXB plus MDXD divided by the sum of the masses. And the y coordinate of the center of mass should be similarly summation My divided by summation M for the 3-particle system. So this point's coordinates, A's coordinates will be, B's coordinates are 0, 0. But what about A's coordinates? A's coordinates are L by 2, root 3 by 2L. And D's coordinates are L, 0. And also the masses, B's mass is M, A's mass is 2M, and D's mass is again M. So you apply all this in this formula and you will get the position of the center of mass like this. You will get XC as L by 2 and you will get YC as root 3 by 4L. Okay. So first just approach this problem from this method, which is the systematic formula. Then we will see how to use a symmetry method and use some kind of shortcut here, because the two mass. So using the symmetry that B and D are of same mass, okay, we can use this.
Done, sir.
Done, sir.
Done, sir.
Sir, done.
Done, sir.
So all of you have understood this by this method. Now next, let's see how we can use symmetry. Okay, so when you substitute here, you get like 2m into L by 2 plus m into 0 plus m into L divided by total mass, which is 4m. So that gives you the x coordinate as L by 2. And when you substitute this, you get 2m into root 3 by 2L plus m into 0 plus m into 0 divided by 4m. So that gives you the y coordinate. And from that, you can see that the position of the center of mass is X. So this is the general method. Now we can also use symmetry. Now let's see how symmetry can make life simple in this situation. So what we can do is that this system consisting of the 3 particles, we can split it up. Like we can, for the work of the center of mass, we can do it in 2 parts. First, calculate the center of mass of B and D as a system. Okay, so B is a mass m here, D is a mass m here, and A is a mass 2m over here. Okay. So first what we do is we understand that this one has a center of mass here at the midpoint. This is center of mass of BD as a system. So next we can say that this is therefore equivalent to replace the 2 particles BD with a particle of mass 2m, that is the total mass B plus D, but located at their center of mass. And then A is also 2m. Now for this system center of mass, we are at the midpoint. So this height is root 3 by 2L. So this height will become root 3 by 4L. Half of this, okay, and here this will be L by 2. So you can understand the position of the center of mass. Okay, so hope this method is clear also to all of you. Okay, so with this we conclude today's first session of center of mass. Please make a note of this, and tomorrow we will see more examples. We have a lecture in the morning, so it's almost in continuation, just about 13 hours before our next lecture. Okay, so we'll discuss further about this from there. In the meantime, also go through maximum questions of circular motion, and also the notes that I've sent, so that in another week's time you can complete circular motion, all questions, discuss your doubts and all that. Okay, that's it for today's session, people. Wish you all the best. Have a nice day.
Thank you, sir.
Thank you so much. Thank you so much.